Good morning again, everybody, and thank you for joining this webinar. And today we're going to talk about simulation, and in particular, how simulation may help in the design of washing machines. You see from my title that I'm going to show two different approaches combined together to get the maximum in prediction of behavior of washing machines. Why this topic? Washing machine is an important area of appliance sector because this is probably the first appliance that was introduced in people's houses throughout the years. We have two typical architectures for this machine. Horizontal axis, which is mostly sold in the Europe, something in Asia and America, and the vertical axis architecture, which is mostly sold in North America and Asia. Different types of machines, but the goal is always to shake the laundry to get it cleaned through a thermal-chemical process. This machine has a high impact on the environment because it uses a lot of water, because it's made by different materials and consumes a lot of energy. So designing well this kind of machine is a driving topic, because if we can save something, making a good design of the machine, we help the environment. And this is a driving topic in manufacturers, because they need to evolve the design to get better products using less material, possibly making them cheaper, and so on. Let's start talking of dynamics. The focus today is on dynamics and fluid dynamics. So the washing machine is really a dynamic system, and it's not a simple dynamic system, because the dynamics of a washing machine is highly nonlinear. In the body that moves inside the washing machine, we have the combination of gyroscopic effects, which is something that may stabilize the motion. We have some friction, because all washing machines include dampers, and they are not as simple as they look like. Friction dampers have a very complicated behavior connected with temperature and motion amplitude and speed and so on. And then we have some connections Rubbermaid between the cabinet and the moving body, the tub. And this bellows, the main one is on the front for horizontal axis machines. This bellows affect dynamics a lot. Not only, the system is somehow uncertain, because you never know what's the level of imbalance that it's inside your rotating drum. The shape and the position of the laundry is completely uncertain. And you may have also uncertainty in certain material properties, especially if you deal with plastic components. You may assume they have isotropic behavior, but this is not really true. This affects stiffness, and when you get to simulation in a high-speed range, so NVH domain, this may affect your results. So it's complicated, it's uncertain. It's really three-dimensional, because in the moving object, we have full coupling of translations and rotations. One of the design drivers is the motion of the suspended body inside this cabinet, and the suspended body is surrounded by not uniform clearance. So even the shape of the motion is important, because we're not moving in a sphere, but in a place that is fitted with other components you don't want to hit. So everything is moving in space, 3D, and the shape of the motion is driven by the tensor of inertia and the type of exciting loads. It's a complex project. Manufacturing a washing machine is definitely difficult. To make it good, to make it cheap, because many solutions, many design solutions are expensive or uses too much material. So getting this system stable and meeting the requested performances is difficult. But we have some help from computers today, and we can spend this power to design our machine to meet our requirements in the two ranges of interest. In particular, at low speed, it's the area where the suspended body crosses the resonance frequency. So in that area, we want to limit the motion of the suspended body, to not hit the cabinet, to not have the washing machine jumping on the floor, and so on. Reversely, in the high speed range, which means at the end of the spinning ramp, we want to reduce the noise, we want to reduce the vibrations, also because the vibrations are responsible of let's say, a walking attitude of the cabinet, because it seems to slide on the floor, and it's due to vibrations. These are different requirements, low speed and high speed requirements. And for the designers, the goal is to make it for both. We have several ways to get it done. Of course, the priority is optimizing the dynamics. We will see in a minute what it means. This is the first thing to do, because we spend effort in obtaining a good design, but the product we make is substantially same cost, same amount of material, and we use the same or less amount of water. So this is absolutely the top goal for designers. Second, we may add to this system some devices that partially compensate the unbalanced loads inside of the rotating drum. And this helps a lot, because this stabilizes the dynamics, and we get a good behavior in a, let's say, easy way. So optimizing dynamics first, adding balancing devices second, and the third remedy to get a good dynamics is, of course, to increase inertia of parts, which means adding mass to your tub, to your counterweights. It's the easiest way, but it's also the most expensive, and let's say the less smart way to make a good appliance. Let's start from the dynamics, because it's the first brick to build this house. And dynamics means basically these slides from Newton's equation. We have our system, it's a second order system, and the excitation is an harmonic excitation, and the response in amplitude has this expression. And it's very easy what we need to do. Either we reduce the force amplitude, and this is the area where we work with the control system, or we add those called balancing rings, so the balancing devices to reduce the force amplitude, or we work on the system, on the mechanics side, by optimizing the suspension system, which means a combination of spring and dampers to control the motion, or we increase inertia. We already told this, so putting heavier counterweights is always a solution, although it is expensive. And adjusting damping is together with spring the suspension topic. So apparently very simple, but we still we need to not forget that this is a 3D system. So we have at least 6 amplitudes that are combined together in defining the resulting motion, and trying to solve this by hand or analytically is almost impossible, because all effects are combined. There are, as said, many nonlinear factors affecting the output. So we need something more. And this is the area where the simulation comes. So we need to have a combination of a multi-body simulation Multibody simulation is born for this stuff. So it's the way to replicate how interconnected bodies move in space under the action of forces. It's the way we solve that equation that I've shown you before, many of those, of course. And in this way, we predict the motion of our system, and we understand why that motion has that shape, that amplitude. But of course, as we said in the introduction, our appliances are dealing also with water in this case. So we have also fluids. And these fluids may be just driven by the mechanic or collaborate in the definition of the final behavior. In this case, we are approaching the fluid dynamics in an innovative way. It's called particle-based CFD. The difference with respect to the classic approach to the CFD is that here we don't need to create a mesh in the fluid domain. We can just discretize the fluid mass through these moving domains. We call them particles, but actually they are moving domains. And we integrate the Navier-Stokes equations. So we are doing real fluid dynamics in these moving domains. This approach is quite innovative because it's very, very suitable for those fluids that are interacting with moving bodies, with moving boundary conditions. So the two approaches, multibody and particle-based CFD, can mix together to make possible things that were not possible before. Just a few words about the two tools that we are using for this webinar. RecurDyn is a multi-body software. It's quite a strong tool developed in Korea by Function Bay. It includes a particular solver that has been designed to handle dynamic problems in a large frequency domain. So this solver is suitable for a regular multibody, but also flexible multibody. It's quite easy to use due to its nice interface. It's very versatile because the software includes an environment for customization. If you are a good programmer in Visual Basic, C#, or Python, you can literally extend the capabilities of the software and create your own pieces of software. Otherwise, you can just use the languages for automating operations. And it's a very open software because it's a multi-body platform that can communicate with other tools to enable real multiphysics. In particular, the communication of RecurDyn with third-party applications can be done using, can be done through the FMI standard, and which is very common among tools in the market. But concerning the communication with fluid dynamics and with particle works, RecurDyn has a proprietary interface that has been developed with Prometheus software, the manufacturer of particle works. And this interface is the key because it's very efficient and makes it very easy to get this coupling running properly. RecurDyn is very strong with contacts, with flexibility. In particular, it features linear flexibility. As usual in multibody, flexible bodies are modeled using component mode synthesis. But we also can include nonlinear flexibility, which means largely deformable bodies, nonlinear materials, and plenty of contacts. Of course, we have the possibility to implement controls, and this is very important for appliances because controls, especially in a washing machines, are the key to stabilize together with the other devices we will talk in a minute. And RecurDyn also has an optimizer inside to drive parametric model towards objectives that you need to define up front. Particle works, we told something already. The key here is that it relies on this moving particle simulation method. There are other tools in the market with sharing this approach of moving domain, but moving particle method as something more. I'm not a specialist of CFD, but I can tell you that the other methods have some limits. ParticleWorks has not, due to this innovative approach. It's quite easy to use, and even the combination with RecurDyn is very simple to be set up. The solver of ParticleWorks is extremely efficient because it runs on GPU. It exploits a lot GPU's calculation, which means that you can get CFD solutions in short time without needing an expensive hardware equipment. And it's opened. As said, even ParticleWorks can talk to other software to make possible multiphysics. And in particular, the most efficient connection is with RecurDyn because the interface was developed together with FunctionBay. So these two applications are born to run together where this is necessary. Talking of washing machines, we need first to make our multi-body model. So we put in the model everything we need, all the bodies we need, the bearings with clearance, the dampers, and for dampers, you can implement any type of formulation you may know from experiments. Bushings, rubber bushings, you may have characterized in lab. Springs, rubber bellows, you can include the bellows as flexible bodies. In RecurDyn, you can do this because we have this full flex approach that allows you to implement nonlinear flexibility natively, or you can use simplified ways to implement the bellows. You can include your transmission, of course, between the motor and the drum. And then, right side of my slide, we go to the most sophisticated parts. We can implement motor and control system. This can be done directly in RecurDyn, where we have a tool called CoLink. It's a, let's say, simplified edition of MATLAB Simulink. Or if you have MATLAB Simulink control system, you can connect it to RecurDyn. This is very easy through an interface that has been designed for this purpose. Besides the regular things, we have the possibility to implement balancing ring, and we will see in a minute how they work. And this requires co-simulation with ParticleWorks because balancing ring includes fluid. And we can also simulate the sloshing fluid inside the washing machine, again through co-simulation. This model, the value of this model increases a lot if we add the parameters that we can play with later. Parametric models add a lot of value to engineering approach. When I say parametric models, I mean that we can do this, we can change these properties, and I'm showing here how to change stiffness, damping, or inertia, just playing with numbers because we define upfront the coordinates of the attaching points or the main size of the counterweights. These changes are driven by numbers, which means that we can automate this process, and automatic optimization is really the winning method to do this. Of course, here it's not just a matter of numbers, because we play with the numbers, but when we change, for instance, the position of the springs, we are changing the stiffness matrix. So we are directly going to change the way this body will move. And it's not obvious to see the result of this without simulation. You need simulation to see what happens. Concerning the connection with the control system simulator, I told you already, you can use MATLAB Simulink or RecurDyn CoLink to do it. There is no difference except the fact that RecurDyn CoLink is inside RecurDyn. MATLAB Simulink is a third-party tool, but the connection is done the same way. You set a number of plant, we call them plant output in the mechanical model. So these are measuring points. You can read the positions, the speeds, accelerations, whatever you need to read from the model. and you pass this information to Simulink or Colink, the control system does the calculation of certain outputs, and these outputs go back to the RecurDyn model. Normally, these become dynamic inputs such as the torque or forces. For appliances like the washing machine, this is the process done for controlling the torque at the motor. And the control understands what's happening inside the washing machine. For instance, reading the current absorbed by the motor. And then it calculates how much to apply to the motor to increase the speed or reduce the speed and so on. This is done automatically, so the connection is done automatically and is preserved throughout the simulation at prescribed sampling time. When I say I want to optimize dynamics, I want to get this to objective mainly. We don't want that at load speed our tab or counterweights touch our cabinet, and the RecurDyn software allows you to measure this relative distance between complex geometries and during the simulation, of course. So we can play with the springs and dampers and shapes to avoid this from happening. Or at high speed, we need to walk on the parameters to avoid this walking of the cabinet. Again, this is a matter of how the body vibrates. Structural frequencies may be important too. So probably rigid multibody for making this simulation is not enough. So we need to turn on flexibility either on the cabinet or the tab, depending on the situation we have in front. But the solver RecurDyn allows you to do that. Then we put everything in an automatic process, because optimizing a 3D complex dynamics manually is too difficult. So we have the parameters and we can run this loop, because at each simulation, we measure our outputs. We understand, the algorithm understands what's happening in the system. Then it plays with the parameters and guides the simulation towards the objectives. And the objectives, we need to set them before starting this process. Once we are done with the, let's say, classic dynamics, which is itself a very complicated reason to do multi-body simulations, we can add something more. And here we start talking of fluid dynamics too. Balancing internal loads is a way to reduce amplitude of vibrations. And in order to do that, we need to add balancing rings to the appliance, to the washing machine. Balancing ring includes fluids, and the way it works, it depends on how this fluid is moving in the balancing ring. But the way the fluid moves depends on the dynamics of the mechanical system. So in order to simulate balancing rings, we need to put together the fluid dynamic simulation, left side, particle works, and the mechanical simulation, right side, RecurDyn. If we trigger the communication between these two solvers, then we can achieve the objective of understanding balancing rings in a dynamic system such as a washing machine. The Japanese fountain is a classic, very simple, very intuitive example from which you understand what coupled dynamics means, because the water here moves according to the container, to the tube, and the tube moves according to the water quantity. So the two phenomena are tightly coupled, are not independent, and you cannot get this system from a standalone simulation in ParticleWorks or RecurDyn. You need them together. The communication works in the same ways we have seen before for the control system, because ParticleWorks is running in GPU and provides the fluids loads on the walls. The walls are all the surfaces that the fluid is touching during the simulation. These loads are transferred to the mechanical model, so are read by RecurDyn, and RecurDyn uses the loads to understand where the walls are going, because it's integrating the equation of motion. As a result, RecurDyn knows where these walls are, what's the speed of these walls, and this information is passed back to Particle Works because the fluid problem needs boundary conditions to be solved properly. This communication happens at each time step, at each sampling time we establish up front. So the two problems are solved together, and we have this multiphysics simulation, fluid dynamics and mechanical dynamics together. The way to connect the two software is very easy. We create the MBD model in RecurDyn as usual. It may feature rigid bodies, flexible bodies, who cares, because the interface is open to everything. Then we created the CFD project in Particle Works. We select our walls in RecurDyn. And when we select the walls, we have some differences between rigid walls or flexible walls. For rigid walls, we create literally a mesh, because this is the way to transform the CAD into an object that later Particle Works can read. So we mesh the surface, and we can adjust the size of these tessels placed on the surface. If the body is flexible, we use the mesh itself to create this information for the Particle Works solver. Then we move this bunch of information to Particle Works. Then we go back to Particle Works and we set all the CFD inputs we need, such as the fluid properties, the wall properties, the domains for the CFD solver. We set the solver settings, which are particular because it's the moving particle simulation method. We turn on the connection and we just press solve, and the two solvers starts working together and communicate at each time step. I made this process for an horizontal axis washing machine just to show what happens. And so I created my model. This is simple geometry I found in the web, so it's probably not really a good design for a washing machine, but it's enough for our purposes. This includes everything. So we have the tub, which becomes a surface to contain water. We have the drum with some holes that is moving in this water field. We have the glass with on the window, because we need to close, of course, this fluid domain. We have the lifters with hose that will go inside and outside the fluid mass. And you may recognize there is also a flexible bellow. The geometry here is super simplified. It looks like a cone, but the purpose is to show that we can include a flexible body in this co-simulation. This is a fully flexible body made by shells, and we are going to use this shell to contain the water, because the full domain for the water has to be closed. We don't want to have water going out. So all of these parts have been considered for the co-simulation. So I first created the MBD model, then I created all the surface meshes that become walls for the CFD problems. And then I packed it all together and passed this information to Particle Works. In Particle Works, this is a CFD domain. You need to set the properties of the particles, such as the size. Size is probably the most important property because it definitely defines how big your CFD problem will be. You set the fluid properties as per a regular CFD simulation. So density, viscosity, surface tension, and other properties depending on the fluid type. In this case, it was water, so just the default values were enough. Wall properties, it's possible to set the roughness of the surfaces and some other parameters to control how the fluid interact with the walls. Then some settings for the solver to play with implicit or explicit solvers and coefficients to control convergence. Very simple. A very few numbers are necessary here. And then you don't need to do anything else because this model is going to run together with RecurDyn. So all motions for the walls are coming from RecurDyn, including the motion of the flexible elements for the bellow. And then this is what you get at the end of your simulation. This was a 10-second simulation, so not so long, showing what happens when the drum rotates and the lifters go into the fluid domain. This took some time on a quite old GPU. You see, this is a Tesla P100 from 2016. So today we have much better hardware, but I used this for this to running the example. And this included 530,000 particles. The size was chosen because we have some holes in the model and I wanted to have the particles growing through those holes. And in fact, you see the fluid is going in and out of the drum and it's affected by the lifters, and the lifters also collect the fluid and release it through the holes. Then, of course, there are plenty of options for post-processing to watch where the fluid is going and to measure pressure, velocities, and so on. As usual for a fluid dynamic simulation, in this case, it's a co-simulation, but the post-processing that you can perform is basically the same that you do normally in a CFD environment. We said a few slides ago that one way to get a good washing machine, or at least to stabilize our washing machine dynamics, is to add some balancing devices. And one of these options is represented by the balancing rings. Balancing rings are empty structures, empty rings, partially filled with water that are fixed to the edges of the rotating drum. In this slide, I'm showing where the balancing ring is mounted on a vertical axis washing machine, but the horizontal axis version exists too. But just to talk of the topic, let's consider this. So it's like a tube, a torus, empty, where we put some water. Its dynamics is somehow magic because due to the fact that we are shaking the system, it's rotating and shaking at the same time. It's rotating in the center of rotation is not coincident with the geometrical center of the ring. We have that the inertial forces that are acting on the fluid slowly push the fluid in the opposite direction with respect to the unbalanced load inside the drum that is causing this eccentric motion. As a result, after a while, we have our original unbalancing load inside the drum, and we have the water in the balancing ring that is exactly on the opposite side. So the total unbalanced load is lower than the original one because this water is somehow compensating. As I told you, this requires some time for the water to go from the initial configuration, let's say flat, to the final configuration where the water is packed on the opposite side with respect to the unbalancing load. So it's really a dynamic phenomena. And the only way to simulate this is to have the fluid dynamics solved together with the mechanical dynamics, because the two things are affecting each other. It seems a simple problem, but in reality, it is not, because if this fluid is moving not as we want, it may happen that instead of reducing the total unbalanced load, it increases the total unbalanced load. So it gives an opposite effect. We want this water to move in a certain way. We want the water reach the desired position in the desired time. We don't want it goes in another position, or at least just in a limited way. How can we obtain this kind of result? Well, in the past, the only way was to do experiments, maybe using transparent rings and the cameras to watch the fluid, to understand why the fluid was moving in a certain way and not in another way. Because inside the ring, there are internal walls, and these walls are designed to drive the fluid and to constrain the fluid in certain situations and leave it free to move in other situations. So designing the ring is really tough because you need to play a lot with the sections in numbers, positions, and shapes to get the desired result. This was the past, because today, due to the fact that we can simulate dynamics of washing machine and fluid dynamics inside the ring, we can do this in simulation. And the simulation provides more than experiments, because look at this, you have a clear view of what happens inside. This is a real machine, was simulated in Korea by Function Bay. You see that the shape of the fluid inside the ring, it looks like a saw teeth, because there are the walls constraining the fluid. And the purpose is that we have to constrain the fluid at low speed and get it moving slowly to the final position for compensating the unbalanced load at high speed. Then, as said, once you have the model, there are plenty of different post-processing processes that you can start, looking at the fluid in different ways, making measurements, understanding if the viscosity is good or not, so you can change parameters of fluid and repeat the simulation, or you can play with the walls and play a lot until you reach the desired behavior. In the end, you always need to check the system in laboratory. But in this way, you just go there for a validation, for a final validation. The design can be fully digitalized using simulation. This is another different post-processing of the same simulation. For instance, on top right, you see the section of the ring. So you see how the fluid is thin or thick depending on the position, because the drum is rotating. I did a model in the past also for horizontal axis machines. The process is exactly the same, and sometimes these rings include also steel spheres. No problem. These are bodies for RecurDyn, and in RecurDyn you can set contacts between the balls and the walls, and then you can include any type of fluid. In this case, it's more similar to oil than water, because the purpose is to dump the spheres. But the simulation you get is exactly the same. And after a while, you will observe your spheres on the opposite side of the unbalanced load that has triggered everything. You can use Particle Works in combination with RecurDyn also for this kind of simulation. This is the agitator on bottom of vertical axis washing machines. In this simulation, the tub is not moving, but of course, in reality, you run this simulation with the moving tub and you give a look at the water behavior too. We are done for the day, for the webinar. So the message I would like you to take with you is that we have today tools that allow the simulation of washing machine at very high level, including any aspect of the mechanical dynamics. And this is the domain for RecurDyn for multi-body simulation. But we can also include the behavior of fluids, and we can simulate them together, which is really an added value that was not possible before. The interface between RecurDyn and Particle Works is so optimized that the efficiency is unbelievable. We don't need to go through FMI standard or other inefficient methods. Here we have a native connection between the two. And I think that the phenomena that you can replicate in simulation are very, very valuable aid for the design, because you can check fluid sloshing, balancing rings, and other aspects combining the behavior of fluid and the behavior of mechanics. I hope that this was interesting for you, and in case you have questions, I'm here to answer them. And yes, I see a question here in horizontal axis. Are used ball balancers? Yes, yes, I've shown the example, so I think the question was made before my slides. Yes, we can simulate that too, because it's again a mechanic plus fluid dynamic combined problem. We have more bodies, but we are talking of limited numbers compared to the potential that RecurDyn can solve. So the answer is yes, we can simulate ball balancing rings, including oil, water, or combination of, no problem at all. If there is some other you want to know about this topic, I'm here, but you can always send an email to EngineSoft, and I will be more than happy to provide further information for you. So thanks a lot for joining the webinar, and I wish you a pleasant day. And thank you for your patience. Probably my English is not excellent, but I'm sure you have understood the value of the tools and the approach that I want to show you today. Thanks again.